Okay, so now let's go to the application of flux that's most commonly used, which is flux through a surface. So I can use this when I'm talking about the amount of water that's flowing through a net, or if I want to, or the rate of that water's flowing through a net. I can quantify power of solar rays that are hitting a solar panel. There's all types of things that I can use flux to help me capture. And so we're going to call this either the flux integral, or sometimes they'll just call it the surface integral and of a vector field. And we define this to be the integral over the surface now of f dotted with n. And now we're going to be using d capital S because we're integrating over the surface. And so here, S needs to be a surface that's what we call orientable, which means it has two sides, as opposed to a Mobius strip, for example, that's not orientable. It also needs to be what we call smooth, which means it needs to have a tangent plane at every point, so you can't have any like sharp corners, except possibly at the boundary. And then we need to define what we mean by n, because n, again, is going to be a unit vector that's normal to the surface, but we have two choices for n. So we, in this surface picture right here, you can see we could either define n to be up, pointing up, or pointing outward, or down. And so we need a convention so that we're all talking about the same thing when we say whether a flux is positive or negative. So either it'll be clear from the physics of the problem, like I'll say what's the flux through the opening of this pipe, and then it's really clear that I'm asking you to make your normal vector pointing outward through the opening of the pipe. Or if it's not clear, then the convention is that it's going to point outward from a given curved surface. So in this picture, the normal vector is pointing outward from this curved surface, as if, what I picture is if I were to close off that surface, if I were to continue this yellow surface and make it, say, like an entire ball, then I want my normal vector pointing outward from that enclosed and solid ball. And so we say that a closed surface that encloses a 3D region has a positive orientation if we choose the end that points outward. And that's going to be the default. We'll just say what's the outward flux, or the surface has a positive orientation, and that's kind of to help us realize which way we are defining the normal vector. Okay, so this blue surface here is closed because it's like this kind of closed weird ball shape slash kind of like a lima bean shape, but we would define the normal vector at any point to be the one that's pointing outward from the surface here. Okay, so what's cool is we can also compute the flux of vector fields such as electric and magnetic fields, even though there's no flow actually taking place. So this idea of thinking of things as moving in vector fields is usually just helpful for us to visualize it, but we can talk about flux even for things that are not moving. All right, so how are we going to calculate this? In good news, we know how to calculate surface integrals from section 13A, and so now we're just going to follow along with what we did there. If you recall, first we started by writing the surface as a level surface of some function of 3 variables. And so even, let's go up to this surface up here, and we can just imagine that we're calling this surface g of x, y, z is equal to some constant. Okay, and then we're going to find n. So we know from the last chapter that the gradient of g is going to be normal to the surface. And so we're going to choose n to be either this gradient or the negative gradient, depending on which one points outward. So you're going to choose this so that it points outward from the surface. Okay, and then we're going to, ultimately we want to change variables and put it just in terms of 2 variables, not 3. So you choose one of the coordinate planes that you're going to put everything in terms of those variables. You're going to project S onto the coordinate plane and find p hat, just like we did. And then ds, just like we proved, the first section 13A is going to be given by the magnitude of the gradient over the absolute value of the component of the gradient that's pointing in the direction P, and then dA. Okay, so let's put all this together now. That means that when we have f dot n ds, that things are going to simplify, kind of similar to what we just saw with flux across a curve, where those, if you remember flux across a curve, our speed was canceling out in the numerator and the denominator, and now here I have the magnitude of my gradient that cancels out in the numerator and the denominator. And so then my integrand is then just going to become the dot product here between f and either positive or negative gradient, depending on your orientation, and then you'll just be left with this. So then, as you recall, there's still some steps. We then still have to rewrite the integrand just in terms of 2 of the 3 variables and determine the limits of integration based on the region you've projected. But once you do all of that, you will have switched this to a double integral over some region R in the plane where you've projected, and you will be able to rewrite f just in terms of variables from that plane, and you'll dot that with either, we're writing plus or minus, the gradient, and then we'll have times 1 over this scalar component, magnitude of the scalar component of g in the direction p, and then dA. Okay, so let's try this with an example. And before we move on, I do want to make one more note that this is the notation you're going to see in the book, but there's also a shorthand notation that we will use. So sometimes we will just write this as the surface integral of f dotted with ds and write this as a vector. And this, again, is just shorthand notation. It literally is meaning this corresponds to this, and we're just writing it in shorthand. And then, side note, in physics, you've probably seen these, but oftentimes they will write it as f dot dA. We're still meaning the same thing. So all of these are asking us for the flux of this vector field across the surface. So that's happening in physics. Okay. All right, let's do an example.